Hi, everyone. Welcome to Foresight Molecular Machines Group. I'm really happy to have so many of you here. We're really delighted to have Charlie McTernan here today. He will be discussing building from biology, peptides as building blocks in supramolecular chemistry. Thank you so much for joining here at the Francis Crick Institute, which is one of my favorite institutions. Really, it's an absolutely wonderful one. And I'll share a lot more info about you in the chat for people that want to read up on your work. But I think you're the best one to explain it to us. Without further ado, please take it away. Thanks a lot for joining.
Thanks very much, and thanks for inviting me here to speak. So I'm Charlie, and I lead a group of supramolecular chemists at a biological research institute, the Francis Crick, that we've just been mentioning in central London. And we work at the interface with biology, looking to explore how biological techniques can impact supramolecular chemistry, and supramolecular techniques can impact biology. And, not advancing my slide. There we are. We work in a range of different areas, building macrocycles and retaxanes from peptides to act as artificial, specific, and biological binders. We work on transmembrane molecular machines, which use orientation provided by a membrane environment to generate function, and on synthesizing non-specific protein degraders using supramolecular chemistry. But today I'm going to focus on talking about some of the work I undertook during my postdoc, looking at creating novel nanostructures and binding sites, and also work my group's doing using biological building blocks, peptides, to create supramolecular structures, methylpeptidic cages, and either built from chains of oligoproteins, which are amino acids, functionalized with metal binding residues, and a program to assemble into precise three-dimensional nanostructures. But before I go into detail, I just want to say a few words about why we're interested in this. So as supramolecular chemists, we're often inspired by nature, and we're looking to create functional architecture to the nanoscale. So of course, looking at a functional system of nanotechnology, that is biology, makes a lot of sense. And in my group, we're particularly interested in self-assembly, the programmed assembly of smaller subunits to generate larger functional wholes. And biology makes great use of self-assembly, for example, in the generation of viral capsids, from smaller, simpler repeating subunits that are programmed to come together to perform a task, here encapsulating, protecting, and delivering genetic material. And of course, this has inspired a wide array of research into the generation of artificial structures with defined internal cavities that mimic viral capsids and enzyme active sites and are able to encapsulate and transform cargoes. They're built from metals and rigid aromatic ligands and generate defined nanospaces. And the properties of these nanospaces can be drastically different from the surrounding media, creating highly active catalysts, such as this cage in the top left, which catalyzes the Nazarov reaction at rates comparable to those achieved by enzymes in different reactions, and enabling stabilization and reaction and isolation of reactive species, such as this cage in the top right, which can encapsulate white phosphorus and render it stable to air for months at a time, rather than being pyrophoric. Finally, you can create extremely large cages, such as these cages on the bottom here, which can encapsulate entire proteins and render them stable to solvents other than water and retain their function. So these are quite useful architectures. So how do we make these structures and control self-assembly? As chemists, we often think about using covalent bonds to build molecules. And covalent bonds are great. They're strong, directional, and reliable, but they're typically formed effectively irreversibly. And this can cause issues in the assembly of large systems, as errors in the assembly process can't be corrected. As such, when creating self-assembled architectures, we typically reach for more dynamic bonding strategies, either weaker intermolecular interactions, or in our case, coordination bonds. And coordination bonds between donor ligands and metals can be strong as covalent bonds, but also dynamic under the right conditions and retain the strongly directional binding of covalent bonds. And we can leverage this to create highly stable final supramolecular architectures in excellent yields by harnessing error correction in the assembly process. So how does a typical metallo-supramolecular assembly process work? Firstly, we have a metal center with, I'm just going to change to a laser pointer, with these vacant coordination sites shown here as triangles. We then heat the system. We then add a complementary rigid ligand with a complementary binding site to these metal centers and heat the assembly to allow it to find a thermodynamic minimum where the coordinated requirements of both metals and ligands are saturated. And with careful design, this can lead to the creation of a single species, such as this metallo square shown here on the right. And this process relies on extensive error checking and the careful control of ligand rigidity and shape to ensure the system can equilibrate to a single correct structure as bonds are formed and broken continually. And this allows the system to explore a potential energy surface and find the desired structure, which would program to be the lowest lying state. And however, one of the key issues of the current generation of molecular cages is that they use rigid aromatic ligands in their synthesis. And this means the cages formed have relatively symmetric and often pseudospherical cavities. This preference, as is an example shown here on the left of a fullerene binding in metal organic cage, contrasts drastically with the precise and targeted binding seen between proteins and their ligands, where precisely folded chains of amino acids generate bespoke binding sites able to interact with exquisite selectivity in a complex and competitive media. And as such, during my postdoctoral research, I became interested in generating more complex functions and more anisotropic cavities from metal organic cages. And the first project I worked on looked at how we could make tetrahedral cages more functional, moving from using fully aromatic panels to integrating functional units in the walls of molecular cages. Here, phosphines. Sorry, my computer isn't coping with a laser pointer, so I'm just going to turn that off. There we are. Which can coordinate metals and catalyze reactions. We first built an aromatic panel with two key functions. We have nitrogen donors at the end of the links, and it's going to bind to a metal, here zinc, which is critical to forming our tetrahedral capsule. And secondly, we have a triaryl phosphine, which remains free and uncoordinated in the final cage. The key idea here was to functionalize the triaryl phosphine after the cage is assembled, and to use this post-assembly modification to change the properties of the resultant cage. We showed the main reaction modes of phosphines were still viable after metal organic cage had formed. We could oxidize the phosphine to form a phosphine oxide shown at the top. We could alkylate it with methyl iodide to form a phosphonium salt and so change the overall charge of our cage. And we can coordinate metals, here forming a linear gold-1 species, to form secondary coordination complexes. But what we were really interested in here was altering the properties of the cage by these post-assembly modifications. And one of the properties we're most interested in is the ability of these structures to bind guests, as binding a molecule within a cage is often the first step to catalyzing its transformation. And we found a class of guests that bound to all three structures, shown here in the green box in the center. And these were mainly non-coordinating anions. We found that the phosphine oxide cage bound an additional array of guests, shown in the red box at the top, and the other cages, which the other cages did not bind, including halides and trifluoroacetic acid. The aerated cage, down at the bottom, uniquely bound cyanide by the externally coordinated gold residue, a binding mode not available to any other cage. And so by tweaking the structure of our cage panels, we're able to control which guests bound in the cavity and around the cavity. But our control was still extremely limited, with most guests binding in all three cages, as the changes in structures were externally directed, and our cavity is still spherical and so less sensitive to these operations. So the next thing we looked at was making cavities that are less spherical. And one of the ways we did this was by moving from using individual metals as the nodes of our cages to clusters of metals, enabled by the use of naphthyridine-based ligands. In our first example, we mixed a rigid triamine, shown here on the left with a nitrogen center, with naphthyridine aldehyde, shown here, and a metal salt, here silver perchlorate. We found that this generated a trigonal prismatic structure with pairs of silver ions at each corner and an extended cavity in the center. And you can see a schematic of the structure shown here on the right, showing the general shape, and that inside two anions are sequestered. Each vertex has a pair of silver ions in close proximity, and each ligand spans three of these clusters. We're able to grow crystals relatively easily, confirming the structure had formed this unusual trigonal pragmatic tube-like structure, where a pair of perchlorate anions were trapped inside the elongated cavity, which has open ends, but is well enclosed along the sides of the rigid aromatic panels. These perchlorates come from the silver salt used to synthesize the cage, or are added to a non-templating silver salt and are essential to template the formation of a single structure. We found that a range of different anions could template these trigonal prisms. And the identity of the anion subtly changes the structures formed, with larger or smaller cavities formed as the cavity adapts to the guest which is bound, and the anions sit closer or further from each other. Hexafluorophosphate on the right, the anions here sit furthest from each other, about 6 angstroms apart, with the perchlorate somewhat closer. The closest approach we saw was in the use of bisulfate, so HSO4, where the anions approach sufficiently closely to approximate a bisulfate dimer, overcoming significant electrostatic repulsion. And inspired by this close approach, we also investigated whether dianions could template assembly. We chose to look at ethane disulfonate, which has a very similar separation to the observed bisulfate dimer, and the strongly oxidizing persulfate, both of which cleanly templated the trigonal prism, beginning to show the advantages of using more asymmetric cavities to bind non-spherical or pairs of molecules. And having formed some elongated cavities, we next looked to see how far we could extend this, using linear connectors rather than the tritopic connectors we previously investigated. By using a substituted diaryl, shown here in the center, we're able to generate some extremely unusual hexameric bundles. I always think these look a bit like wheat sheaves. Here we again add a silver salt and a templating anion. With iodide, we get a silver 4 iodine cluster at each end of the bundle, whilst with sulfate, we get a very strange looking silver 6 sulfate 2 cluster at each side. The overall shape, the hexameric helicate of the organic part, is the same in each case, but with totally different coordination clusters holding them together. So this was somewhat unexpected. We're able to grow crystals of these bundles, and they provide us some insight into the stabilization of the unusual clusters, with a sulfate cage having numerous close CHO contacts, presumably stabilizing the close approach of anions via non-classical hydrogen bonding. And while these tristed wheat sheaf structures were interesting from a structural perspective, we'd actually narrowed our cavity so much that we're unable to bind guests. And so we moved to an alternate ligand system as we've gone too far down the elongation route at this point. So simply by extending our central panel of the first example I showed you, we've got a benzene in the center here rather than just a simple nitrogen. We're able to form a somewhat unexpected double-walled tetrahedron with a familiar silver 4 iodine cluster at each vertex. And here, each face of the tetrahedron is covered not by one, but 2 panels. So you can see these are stacking on top of each other on the same face of the tetrahedron, creating a very tightly enclosed cavity. And it's perhaps easier to see this in this representation at the top right, where we replace the actual panels by these tube-like structures. So you can see a green external panel is partially eclipsing a blue internal panel. Each vertex coordinates 6 separate ligand arms and brings them together, and a small central void still remains. And we're able to bind guests within the cavity here, although we found that binding in the interior was again limited by the small size of the cage. We found that several small ions could fit inside the central cavity, but perhaps more interestingly, we found that we had a secondary binding site formed on the exterior of the cage, where 6 neutral molecules, small aromatics, could sit in a defined cleft between aromatic arms, more closely resembling biological building sites, such as grooves in double-stranded DNA. So before I move on to the work of my kind of current independent research, I want to touch on one more project that I undertook in the Nishka group during my postdoctoral research. So I'd extensively explored how we could vary internal cavities and change gross molecular shapes by using silver naphthyridine cluster chemistry. But I want to also look at how we can use subassembly to form molecular knots. We found that mixing a simple dialdehyde, shown here on the left, with a dianiline, which is linked by a flexible linker, with a specific metal salt, so in our case, the iron or zinc triflate salts, generated a tightly woven molecular knot. And the system was based on a previous report using monoanilines that formed a molecular grid, so the basis of molecular knot, with the same central core. So why do we have to use iron triflate? The crystal structure shows the reason very clearly. The central cavity is bound to a triflate anion, which it fits in pretty much perfectly. And this templates the structure and pretty much completes that central cavity. And the external ion centers shown here each coordinate 2 triflates. So instead of a single closed binding pocket, we have 3 separate and quite open and distinct cavities here. The internal more resembles a kind of standard aromatic box for binding a single triflate, but these external pockets have a metal iron 2, which is also binding 2 triflates, which fit in the cavity remaining due to the internal aromatic box. The crystal structure also allowed us to identify the knot we'd formed as an 819 knot, with 8 real crossing points and some nugatory crossings. One of the really interesting things about molecular knots is that they can be intrinsically chiral structures due to the way that they're tied, rather than any property of the actual thread used to tie them. And we could distinguish the enantiomeric knots we'd formed in our initial system using a chiral shift agent in NMR spectroscopy. So we next focused on finding a topologically selective way to form one hand of the knot over the other. The approach we found to be successful was to install point chiral centers in the backbone using a cyclohexyldiamine shown here on the left in blue and red as the 2 different enantiomers. And we wanted to use this point chiral information to control the topological chirality of the resultant knot. Importantly here, we'd have to transmit the point chiral information from the nitrogen, the cyclohexyl ring, along about 10 atoms to these central metal centers in this inner quadrant to control the overall chirality of the knot. NMR and mass spectrometry confirmed that we'd formed the expected molecular knot, and we moved to circular dichiasm spectroscopy to assess whether we'd managed to introduce topological chirality in our system. We used iron in this system due to the distinctive metal ligand charge transfer absorbances we see, which are far above the range of the normal amide absorbances in the point chiral center in our molecule. Depending on which enantiomer of diamine we used, we see equal and opposite circular dichroism absorbances in the metal to ligand charge transfer region, confirming that we have indeed induced chirality in our central metal centers, and so the global topological chirality of the molecule formed by transferring this information across some very flexible linkers. So by the end of my postdoctoral research, I'd explored the limits of complexity that we can achieve using rigid and flat aromatic panels, and was looking for new challenges to explore in my independent career. We're still limited by the relatively symmetric and often pseudospherical cavities that we're forming with aromatic panels, and by their achiral and flat nature. The contrast to the rich and specific binding achieved by nature suggests that there's still room for innovation in the design of metal organic cages. So cages are normally formed from these rigid and flat aromatic panels. These provide direction to coordination vectors. So at the top left, you've got pyridines, and the coordination vectors are shown in red. And this disfavors the formation of polymeric and non-discrete products by driving the formation of closed structures. They also create a relatively isotropic structure, resembling a sphere, as they present flat surfaces to the interior. They also tend to be rather hydrophobic, which really limits you when you're trying to apply these in biological systems. So how can we create rigid ligands with directional coordination vectors whilst moving away from unsaturated and aromatic systems, enabling a far richer binding behavior and the application in biological settings? Our answer is to use a defined folding of helical peptides, getting the best of both worlds, the rapid assembly of large architectures so valuable in metal organic cages, and the rich chiral and three-dimensional language of peptides. We'd expect far greater water solubility and easy synthesis, enabling diversification. However, we'll be fighting the higher degree of conformational freedom of peptides, which may prove an insurmountable barrier to cage formation. Specifically, our first protocol is to use the defined and rigid polyproline 2 structure as a base from which to build molecular cages. The polyproline 2 structure completes a turn every 3 residues, with an N and N plus 3 separated by 9 angstroms, and they're highlighted in blue on the left-hand structure. The polyproline 2 structure also presents these 2 residues to the same face of the helix, so this is ideal for forming molecular cages. And it's often being used as a molecular ruler due to its reliable formation and rigidity, and is often stable to heating and solvent changes. The structure tolerates substitutions, such as the substitution shown on the bottom right, so proline to 4-hydroxyproline residues, which would allow us to install metal binding moieties. Finally, oligoproline residues are readily synthesized by solid phase peptide synthesis, which is a key advantage for a young group, increasing our throughput and allowing rapid prototyping. So how do we actually build these cages? First, we build our ligand, using solid phase peptide synthesis to combine proline and protected hydroxyproline, with hydroxyproline installed at positions 1 and 7 in our 7-mer chain. We cap with pivalic acid to provide an NMR handle to monitor assembly and folding, and to prevent the amine interfering with assembly. After cleaving from the solid support, we can couple on isonitrogenic acid, so this carboxylic acid-based pyridine, using standard peptide coupling chemistry, generating a folded chain which presents 2 pyridine metal sites to the same face of the helix. Circular dichirism and NMR studies confirmed we are folding to a single polyproline 2 structure in aqueous solution and forming a mixture of polyproline 2 and the extended polyproline 1 in acetonitrile. As such, we explored cage assembly in water because we need this single polyproline 2 structure. So to assemble our cages, we simply add a suitable palladium salt, in our case the nitrate or tetrafluoroborate salt, and shake in water. We found that assembly in these systems is extremely rapid. A palladium 2L4 cage is formed before an NMR can be run, which we attribute to the relatively weak metal ligand bonds due to the para-electron withdrawing groups, these esters para to the nitrogens, enhancing the rate of error correction. So how do we know we have assemblies? The first evidence is from the increasing complexity of the NMRs we generate, along with characteristic shifts and splittings on palladium addition, which we'll come back to later in this talk. The important peaks to focus on here are the pyridine alpha and beta protons, so shown here in red and blue. I'm going to turn back on the laser pointer and see if my computer will tolerate this, shown in red and blue at the top here. And also this tert-butyl residue shown in yellow, which is a nice reporter signal of what's going on in our systems. On assembly, we can see significant downfield shifts in these red alpha protons. So that tells us that we're coordinating palladium, which is a cationic center, and splitting in several environments, most clearly shown in these high gamma CHO, and also the tert-butyl region, where you clearly see 1 peak moving to 2 peaks. We'll also characterize this by Dozy NMR, in which we see an increase in diffusion coefficient between the ligand and cage, corresponding to an approximate 2-fold increase in hydrodynamic radius, and high-res mass spec, where we see clear peaks for the palladium 2L4 species, flying as both the +4 and +3 species. Isotopic distributions matched up well to simulations, and circular dichirism spectroscopy confirms the polyproline 2 structure is retained and is unaffected by cage formation. So having shown that we can form a cage from peptides, we now wanted to make use of the advantages of peptides, their trivial modular synthesis and repeating motifs. And we first targeted a cage with 7 proline or hydroxyproline residues to ensure stable folding in solution, and that we generate 2 full turns of the helix to try and maximize the rigidity of our structures, and so the chances of us forming discrete molecular cages rather than a polymeric mess. We use solid phase peptide synthesis to synthesize a family of ligands with 4, 10, or 13 amino acids. And these were rapidly formed and purified by HPLC, ready to probe the limits of our methodology. Would a sequence as short as 4 amino acids mimic the rigidity of the aromatic ligands so commonly used? And how long could we make these systems before aggregation or the decreasing ratio of binding residues to peptides became an issue? Pleasingly, we found that we could form cages from all of the ligands. Proton NMR experiments confirmed the cages assembled with carriage to 6 shifts in the pyridine alpha protons, highlighted here, and also desymmetrization occurring throughout the ligands. We saw progressive broadening of the peaks as the ligands became larger, which we attribute predominantly to the expected decrease in NMR resolution in larger systems due to slow tumbling. We can confirm cage assembly in each case by high-res mass spec and dosing spectroscopy, with isotopic distributions matching Wells predictions in all cases, and a gradually increasing size, so size is increasing as we go down this spectra, seen through the series of ligands here at the top, and the cages shown here as these bottom 4 bands. As such, we're able to create a family of palladium-2 L4 cages from oligoprolines, varying in length from about 1 to 4 nanometers, simply by varying the number of repeating units in the ligand strand in a manner which is partially analogous to how DNA nanotechnology can form very much larger structures. And this is really a key advantage when building molecular cages, as in typical aromatic systems, this extension is rarely trivial or reliable. We can also tune the shape of the cavity arising by this variation, creating increasingly elongated cavities as we go from these smaller systems at about 1 nanometer to these larger systems at about 4 nanometers long, without changing the width of our cages. So far, we've been talking about these cages as akin to those formed from traditional rigid and flat aromatic panels. But of course, oligoproline chains are intrinsically directional, chiral, and helical, and so are much more complex. The C-terminus is not the same as the N-terminus, and we only use one hand of amino acid building block and so control the chirality of our system. As such, cages formed from these ligands can exhibit distinct structural isomers. And there are 4 potential isomers which can be formed from our helical proline ligands when they assemble cages. Those with all of the C-termini aligned, this left-hand structure, which we call the C, where we've flipped one of these, so one N-terminus at the top and the other 3 are at the bottom, this CN. We can also have 2 up and 2 down in 2 different ways. We can have the C-termini across a palladium center from each other, the trans isomer, CN. And we can also have the cis isomer, CN, where the 2 aligned residues are on the same face of the molecular cage. When starting this project, we had expected to form a range of different isomers as we'd not deliberately programmed isomer control in our systems. However, our NMRs clearly showed that a single species was predominantly forming. So in the proton NMR, we see the tert-butyl as a single peak in the ligand, and the aromatic peaks as 2 doublets, some of which are partially overlapped, with the alpha and beta protons split into C and N terminal environments. On assembly, we see a 2-fold desymmetrization of the ligand, leading to a doubling of the number of signals. And this is particularly obvious in the pyridyl region, where 2 become 4 residues, and also in the tert-butyl region, where 1 peak becomes 2. This is due to our forming separate but equal ligand environments, which is only possible in the cis arrangement of our cage. In the all-up isomer, we'd expect 2 environments for the pyridine at the C and N terminus. In the CN isomer, we'd expect 8 separate environments, as each pyridine is unique. Whilst in the CN isomer, we'd again expect to see 2 environments, simply the C and N terminal seen in the free ligand. Only in the CN cis isomer would we expect to see the 4 environments in our NMR, 2 for each of the N terminal and C terminal pyridines. So why do we see these 2 environments, and why do we expect to see them for these C or N terminal pyridines? That's because the 2 aligned strands are not equivalent. If we look at the 2 aligned strands from this perspective, so face on, and then look down the axis of this ligand metal bond shown here on the left, this C-terminal helix sees an N-terminal helix to its left and a C-terminal helix to its right. If we instead consider the right-hand helix, looking down this ligand axis, the C-terminal helix this time sees a C-terminal helix to its left and an N-terminal helix to its right. As the oligoproline strands are chiral and directional, these are not equivalent, leading to the observed 2-fold splitting that we see. We tried a very large number of crystallization attempts to try to determine the solid-state structure of our systems, but unfortunately had no joy. We turned instead to some molecular modeling, and were able to model each potential isomer. Pleasingly, modeling returned the cis cage as the most stable by a very significant margin, and provided insight into the cause of this stabilization. Only in the cis isomer can the ligands tilt to form this kind of twisted oblique prism, rather than a standard cube, to relieve strain effectively. And you can see this from the misalignment of these 2 palladium centers. Along with the alignment of this carbonyl residue here, which moves to the interior of the cage to avoid clash with this tert-butyl group shown here, creates a lower energy structure only accessible to the cis cage, and it can't be accessed by any other isomer. To confirm the importance of the tert-butyl group in driving formation of a single isomer, we synthesized an analogous cage where the pivyl group was replaced by an acetyl group. The decreased steric bulk of the methyl group led to a significant decrease in the control of isomer formation seen in our system, confirming the importance of the cap in driving selective assembly. So the cap is down at the bottom of our systems shown here. That's the R group. And you can see here, particularly in these gamma CHO region, we've gone from having predominantly 2 peaks to having about 4 and some broadening in the rest of the spectra. So the capping of our ligand strand is having a significant effect on isomer control. We got a much more drastic effect when we looked at moving from a para substitution, as shown here, to a meta substitution, as shown here in our pyridine. Whilst high-res mass spec confirmed that palladium 2L4 structures still predominate, the proton NMR clearly shows that we formed a wide array of different structures and different isomers with very little control. And this supports our molecular modeling, with the tert-butyl group important to drive orientation of the N-terminal carbonyl, but the paraligand important to set the stage for a tilt-relief strain, favoring the cis cage. We think the tilt-relief strain is the most important factor, as shown by the dominant effect on isomer control of meta-substitution, as compared to changing the capping group. So having explored potential reasons for this unexpected selectivity, we next move to explore the properties of our cages. We found that the enclosed cavity is roughly 4,000 cubic angstroms, and encouraged by this, proceeded to investigate the guest binding ability of our cages. We also create a very patterned internal cavity as these helical structures wrap around and provide a chiral and differentiated structure that guests could bind to. So we hope for more interesting binding behavior in our previous pseudospherical systems. We found that a wide range of interesting molecules were bound in our system, from traditional anionic and hydrophobic guests to dipeptides, and a range of therapeutics, including molecular glues of the thalidomide family. In some cases, we could confirm binding by high-res mass spec, which is often indicative of strong associations, and other associations were monitored by NMR titrations. We're excited about exploring the properties of these unusual systems further in future work, particularly in kind of drug delivery angles, and looking at how we can actually control this chirality. So one of the unexpected aspects of our synthesis of metal peptidic cages is that we get selective formation of a cis-aligned isomer of cage. We wondered if we could exploit the modularity of our system to force the assembly of a less preferred isomer. And to do this, we tried to install additional metal binding sites in the interior of our 10-mer ligand shown here. So we had metal binding motifs either at positions 1, 4, and 10, so aligned on the same face of the helix, or also at 1, 7, and 10. So forming a small unit either at the N-terminus down the bottom, or the C-terminus as shown here. So we'll have a larger unit and a smaller unit here. And this should notionally align our helices, so we've got the C-termini all at one end. We found that on palladium addition, both the C and N-terminal cages formed with high-resolution mass spectrometry showing conversion to a single species. But we got a bit of a shock when we looked at iron Mars. With the C-terminal ligand, addition of palladium leads to clean formation of a single species in a single isomer by NMR. But with the N-terminal ligand, we get completely different behavior, which is rather unexpected as they're very similar ligands, and instead form a complex mixture of isomers with almost no control. When analyzing the C-terminal cage, we had another surprise when we found that we'd again formed the cis cage. We'd imagined that this would be geometrically forbidden. So we take these two very similar ligands shown here, just varying the position of this internal coordinating group. If we have an N-terminal smaller group here, we get a complex mixture of palladium 3L4 cage isomers. But if we take the C-terminal ligand, we get a completely different effect. And instead of the expected all-aligned isomer of cage, we again see the cis isomer of cage. So it's likely that the N-terminal isomer disfavors cis cage formation but doesn't favor anything else, whereas the C-terminal isomer doesn't sufficiently favor the all-aligned product, and this preference for cis cage and tilting dominates formation. We think this is to do with the fact we're misaligning our registries when we tilt these cages, so the cis cage can still dominate. And we're investigating this further at the moment. To sum up, we successfully synthesized a new class of metal organic cages, metal peptidic cages. And this new family is easily tunable with a broad range of sizes synthesized. We see excellent isomer control emerging unexpectedly by the use of complex building blocks. And host guest studies show association with a range of guests, including therapeutics. You can read all about it on our preprint at ChemArchive shown here. And you can also scan this QR code, which should take you directly to the paper. So in the future, we're looking to install catalytic functionality within the central cavity to start to mimic enzyme active sites at a very basic level, and to explore how we could use these systems in drug delivery. So with that, it just remains me to thank my co-workers in the initial group during my postdoc, and then my group and my funders. And I'd like to particularly thank Ben, Leah, and Ellen, who actually undertook the work on metal peptidic cages. I'd also like to thank yourselves for listening and coming today, and also for the invitation to speak to you. And I'm more than happy to take any questions. Thank you very much.
Wow, wonderful. I can't believe that you stayed so well within the time limit. And this is really exciting. And Thank you so much. That was quite the whirlwind. Are there any questions or comments from the group? Feel free to just raise your hand if you don't want to pop them in the chat, or if you can't unmute yourself, feel free to just pop them in the chat. Otherwise, I'll just kick us off with a few questions that are usually like very relevant to Foresighters in general, which is, if there's one, I think you tagged that question a little bit already, but if, let's say, someone more junior was like listening to this afterwards on YouTube and was wondering how they could possibly contribute, to the field at large, where would you guide them, and where are open problems that you currently are seeing where you just want more hands on deck?
Yeah, definitely. So I think, supramolecular chemistry really works in organic solvents pretty much exclusively. So kind of hydrocarbon-based solvents. And I think that's a real problem if you want to apply it in biology, because all our building blocks are rigid and flat and they pretty much hate water. So I think a challenge for the field more generally is to try and build systems that can work in water and actually like to be in water and make use of the advantages of being in water, like biological molecular machines do. And so I think we're going to have to re-understand the language of supramolecular chemistry and what interactions work well and which ones work badly to redesign our toolbox of molecular machines and other supramolecular structures to work effectively in water. So I think that's going to be a long-term project for a lot of people.
And are there specific areas that you think are like at least promising to consider here?
Yeah, so I didn't talk about it today, but I really like the idea of putting molecular machines into membranes, because a lot of the current generation, you're floating in solution, so it's hard to orientate them and get collective motion to achieve work. And, some people have done some beautiful work tracking them on surfaces or in MOFs. But I think membranes and alignment of your machines in a very simple and trivial way. And because they're more soft matter, interfacing that with biology is going to be far more simple. So I think there are a lot of unexplored opportunities in membrane molecular machines.
Yes, they come up every time at our workshop. And I think I just like promising, especially in the application angle as well.
So hard to do.
We understand membranes. I guess we have one from Niladri. I'll just read it out for you from the chat. Thanks for the great talk. I'm not sure if I missed this, but what would be the stability of these metal peptide cages?
Sure, no, great question. So we've looked at it in a few different ways. So ligands, the esters on those are quite prone to hydrolysis. So if you put them in solution, they tend to fall apart over the course of hours, which is a major annoyance, actually, practically speaking. But when you actually form the cages, they seem to be stabilized by coordination to a Lewis acid, which we really didn't expect. So these are stable basically indefinitely in normal aqueous solution. You can put them at quite low concentrations, so 200 micromolar, before they start to fall apart, because these are equilibrium structures. So if you go low enough concentration, they do start to fall apart. They're moderately stable to acids and bases. So you can put stoichiometric quantities of acids and bases in and they don't do much. If you go to higher equivalents, you do start to either hydrolyze the esters or outcompete pyridine coordination for the metal. The final thing that is really inconvenient for us, because we want to put them into biological systems, is they absolutely hate halides. So chloride completely kills them. They just precipitate. So that's something we're looking to fix in future systems. But I think this is more due to the intrinsic solubility of these cages rather than any kind of competition. So we've got some workarounds on that, and we think they're going to work out for us. No, thank you.
Yeah. Do you want to describe a little bit more about, future areas that you're currently are excited to consider?
Yeah. So I think, at the moment we're forming helical pillars around these central cavities, but they're still relatively simple. So if you look at an enzyme active site, you've got precise orientation on multiple levels of different amino acids. And we're just sticking prolines in. So compared to a flat aromatic panel, they're pretty complex. But compared to an enzyme active site, they are extremely simple. And so I think the first thing we're going to look at is actually orientating different functional groups. So because of the repeating nature of this oligopolate strand, depending where we put that functional group up the strand, we can control the kind of reactivity we're going to get in the center. So simply by bringing together, say, something Lewis acidic and something nucleophilic, we can start to create very basic enzyme active sites. So I'm very excited about the idea of mimicking function that's been lost in biological systems, because we're very good at, drugging enzymes and proteins to either remove them or just knock out their function. But we're terrible at replacing that function because we can't build machinery that's good enough. So I think it's a very long-term goal. I'd love to be able to sit on my computer, design this little box with different functional groups coming in that I can precisely control to say, I want to catalyze, uncaging this drug molecule or replacing this enzyme that's defective in a certain disease, and then give that to someone and cure that disease. So I think that's something very long term and kind of pie in the sky, but it would be rather cool to do.
Could you just, for perhaps like more lay folks, describe a little bit what types of specific applications it would have, specific disease that you're looking at, or
Yeah, I think the easiest way to approach it would be to think about getting a drug molecule is pretty toxic. So chemotherapeutics, that's normally pretty toxic to all cells. But if you cage some of the functionality on that, so you whack on a group on that stops it being active, and you apply that systemically. If you can get your active catalyst into one kind of cell, which you can do with targeting groups relatively well, you could simply cleave that protecting group. So cut it off only inside those certain cell types. And so something like an esterase activity or a peptidase activity, which is relatively simple to design, but should be tractable as a first step. So that would be the easiest one to go for. Other ones are a little bit harder, but definitely doable.
Oh, that's awesome. How far out do you think that would be? Obviously we have a speculation head.
Like far to know. I think doing it in a test tube of cells, a cell culture, maybe five years out. Getting that into kind of a model system like a rat might be a way off there. But if we could do that in cells in 5 years, I'd be delighted. It would be proof of principle that it's an interesting area that we could explore in going forward.
Okay, awesome. And oftentimes, sometimes pops up as like people in different groups are like asking about like basic AI applications or like other tool applications that they possibly help build, for work like yours. Like are there specific, let's say, tools that have come, let's say, along in the past few years that you've used a lot and that really accelerated your research, maybe from a different field? And if not, do you have requests for tools, that may not be right in your domain, but we're like, if we had this, we could be moving much faster?
Yeah, so that's very interesting. So I think I've been looking with a lot of jealousy at the protein modeling breakthroughs that have been just racing along and massively advancing those fields. But whenever I talk to molecular modelers, they see the metal centers and they run a mile. So it's a very simple one. If someone could just create molecular modeling software that can code with metals, it would be absolutely lovely. I think that would really help us. And I think making some of the AI tools more accessible to chemists. Some of the people in my group have started to play with these to do a little bit of the analysis for us. But it's very much our jobs aren't repeated enough to make it worth it. So the uphold cost of designing something or learning how to do something is quite high, and we don't get enough payback from that. So the central stock of something more advanced that's applied specifically to chemistry, interpreting spectra, or even just taking data from a spectra and putting it into the correct format would be quite valuable in terms of time saving, because we spend a lot of time just doing that. It's not interesting or valuable work, taking stuff from one format, so a visual kind of spectra like the NMRs I showed, and put it into text. So something as simple as that could save, 20% of the working time of a chemist, which would be lovely. And it's very simple.
It should really be possible, like
someone needs to do it. I don't know how.
Yeah, we should be able to do that. Absolutely. Okay, I have lots of follow-up questions here, but Steve had his hand up for a while. So you go, Steve.
I was wanting to know why palladium, and have you done any early work with second period or first period transition metals?
Yes, palladium is basically for ease. It works really nicely in its square planar. So it makes our design of structures really simple, because it's basically just nice triangles. You get something that's going to poke that way and you form an enclosed structure. Lovely, reliable. We've actually looked at going down to platinum to increase the stability of our structures as a first step. We do have some approaches for using more first row transition metals, so iron, cobalt, things like this. But you normally have a cost there in terms of stability of your final structure. So if you're looking to apply it in more biological settings, they tend to fall apart kind of low millimole, very high micromole range, which is too high for what we'd be interested in. You can get around this by things like cobalt-free and things like this. So it's something we're looking at, but we haven't quite cracked how to make tractable structures. And so again, it comes back to this kind of lack of modeling capability for metal centers. They tend to do something weird on you.
Would the uranol ion with the polar oxygen atoms fit into your model?
Well, it would, yeah. I think I haven't dared suggest to my team the use of uranium, but I'm sure they'd be willing, just for the novelty factor. I'd have to do some digging into the strength of those bonds. So I know they have decent axial coordination, but just have to check it out. But it should do, geometrically, it looks good. It's about whether it's stable enough. Perfect, thank you.
Cool. Okay, so more modeling and basically just better tool development that is also easier for, to justify like the expense of like actually learning the tool, to make it either easier to onboard or then also more general purpose, more transferable like between different modalities and so forth. That would be amazing.
And just even the less scientific grunt work if that any automation on that front is really going to accelerate things, because it gives you time to do the more complex niche stuff. So yeah.
Yeah, even like AI tool developers are often just, we need like just better like ways of like even leveraging the data that's out there. And so I feel like there's a ton of work, even just like in data preparation, standardization, like ease of use. And I feel like that will, if and when we solve that, will really speed up progress by quite a lot. It's an unsexy, kind of annoying task to do. It will be a great automate. Okay, awesome. I think one question that I really have for you also is, if you just think about, your work or, your labs and teams work, are there any specific things, if people were watching this and were just like, this is really interesting stuff, where they could help with in particular ways? Or, is there anything worthwhile coming up? Either if you have a paper that's coming out, if you're hiring, you have a new research collaboration that you really want to establish, anything at all that like is just on your mind right now, where you're like, oh, this would be really great to do.
Yeah, we're definitely hiring. I'm going to be hiring a postdoc and a PhD in the next few months. If anyone knows anyone who's looking for roles, that's definitely of interest. Get them to come talk to me. I think it's probably not the right setting, but we're really interested in more biological collaborators who are a bit closer to chemistry. So we can do some of the basic stuff ourselves, but we start to struggle when we get too far along the biological application route. We've got some very interesting stuff coming up on extremely strong binders, so subfentamol binders, we think, that really like cationic species. So if anyone has any interesting angles or things they'd like to remove from somewhere that's got a positive charge, that we could help out with that. So we were fishing for interesting angles to take that further. So we're looking at symfabidin type applications, so very strong and specific binding to link together proteins and subunits like that. So those are probably the upcoming areas that are interesting for us. We might need some help out there for.
Okay, cool. What could you specifically make with that? Why focus on this?
Yeah, so I think it's a nice way to link two things together. So we can design something that really likes our binder and a binder that's quite specific for it. And we can put the binding affinity of those at somewhat ridiculous levels, so that if you put them in at sub-picomolar levels, they'll find each other and stick together forever. So I think that could be quite interesting in terms of linking, say, subunits of proteins together. So people use symfabidin, avidin interactions extensively, and also to go fishing in proteomics or enrich a certain protein to figure out what's happened to it inside cells. At the moment, we're a bit limited in terms of orthogonal routes to do that. So you can use streptavidin very well, but if you need to do something else, it's a bit harder. And obviously, when you're using that kind of avidin, streptavidin, they are large systems, and that can be an issue in certain applications. So where you want two small molecule things that are linked together, pretty much anything, I think that's where we're going to have some applications.
Okay, cool. Maybe I'll finish with a few more general questions that folks are often quite interested in, but never really get to ask. So I'll channel them here. We sometimes have these like forms of what are all the questions that you would have liked to ask in the seminar. But one of them is just like a general kind of like assessment of like, how do you feel like your current field is going in general? Have there been any kind of like significant changes over the past, let's say since you've really been in it, positive or negative? And, just to get sounds so ridiculous, but like a vibe check on the field, or, just is there anything for new people trying to enter to know, or even like for, funders focusing on the space to know, how has it field changed in useful and unuseful ways, and where do you see it going? Is there any specific?
Yeah. So I think it's beginning to mature a bit. I think initially it was very much like novelty factor. We can do this. We didn't know we could do this, and just, hey, this is cool. And I think maybe the last 4 or 5 years, maybe 3 years, it started to do useful things. Very much at a borderline level. There are other ways to do the things we can do, but it is starting to get interesting. And I think probably in the next 10 years, that's going to be the major vibe change of the field. I think we're going to have to start to do something practical in some kind of area. I think there's only so far you can go with just saying, hey, this is cool. You've got to start having some kind of useful application, at least on the horizon. So for me, that's applications in biology, because it's a very high impact field. If you can get it, there's a large payoff to a small amount of compound. So I think people are looking at that, and also people are looking at more industrial applications where you need larger amounts of stuff, but again, it might be more reliable and more tractable. So I think something's going to give there pretty soon, and I think that'll be quite exciting.
Wow, that's great. In the industrial application space in particular, that's definitely a big funding interest, at least pretty nuts. Okay, and final question then, if someone was like entering your field, new, young, talented researcher, is there specific advice, like things that you wish you had learned earlier, where, okay, it's like a good hack, or this is how you navigate the space in particular?
I wouldn't have dropped biology at 16. I'd have taken it a bit further. It would have helped me out a little bit, but I think it's probably too late for someone just entering the field. I think learning more techniques as you go through, and taking any opportunity to learn a technique with a collaborator. So I think, when I was more junior, I'd often, if someone was specialized in something, I'd collaborate with them to get them to do it. And I just, sitting here as leading a group, you really wish you'd just taken advantage to actually just sit with them and learn everything. Even if it slows down your publication rate, knowing how to do all those weird and wonderful techniques actually unlocks a lot of research for you and a lot of ways of thinking about things. Because if you understand a technique, you can see how you could apply it to your problem. Whereas on the outside, it's more opaque to know, is that the right one? Is that going to give useful data? Is that going to help me move forward? So I think, collecting as many techniques and not just collecting papers is definitely a valuable way to think about things.
As long as they're open to, training you.
Yeah, exactly. Find the right collaborators.
Yeah, I really love that. I think it really compounds, and it also probably allows for much more interdisciplinary collaboration, because you're like, oh, okay, we may be doing this and you guys over here can be doing that. Okay, awesome. Is there anything you wish we had asked? Anything like we have dropped the ball on that you want to get out there?
No, I think that was lovely and a great set of questions. So thank you very much. No,
thanks a ton for joining. I really appreciate it. I think you get like a lot of thank you, fantastic presentation and so forth in the chat. Thank you. I really appreciate the time. I really appreciate you guys all joining and your virtual labs. And I'm excited to get this up on YouTube and hope to see you in person eventually.
Okay, definitely. Another meeting. Perfect. Thanks very much.
Thanks, everyone. Have a good one.